So the big problem with SETI is that the universe is big. And when you're searching for some kind of signal from an extraterrestrial civilization, where do you look? What wavelengths do you search in? It's hard to know. But the universe has provided us with a beacon, a way for us to time our communications with each other. And that is bright supernovae. So when a bright supernova goes off nearby, that is a chance for various civilizations to time their communications with each other to say, you just saw the supernova, you know that I just saw the supernova, so why don't you look at my star and see if I have an interesting message to send? And my good friend, Dr. James Davenport, has recently published a paper on this idea as a way to very efficiently and effectively search for messages from other civilizations. So we talk about that and just talk about how the field of SETI has been gaining more mainstream acceptance in the scientific community and how that's really enabling a lot of really interesting ideas, collaborations to come together. And of course, James is on various committees that are working with the Vera Rubin Observatory. And this is, of course, this incredible observatory that comes online next year and will give us this view into the universe, the likes of which we've never seen before. And so if you weren't already excited about Vera Rubin, I promise you, you listen to the last half of this conversation and you are going to be losing your mind with excitement for what's about to come our way. So it's a fascinating conversation. James is an excellent communicator. We have a great conversation both about the search for extraterrestrials as well as what we can expect when the Vera Rubin Observatory finally comes online. All right, enjoy the conversation with Dr. James Davenport. James, it's good to see you again.
Good to see you, Fraser.
Wow, you really sort of grew out your pandemic haircut.
Yeah, why didn't you?
So
what
jealous.
Happened?
Oh, I keep trying. For the podcast listeners, James now has a luxurious lion's mane of hair, and I am still bald. But yeah, so. You sort of, I'm always excited to talk to you, and, you're one of those great YouTubers who is also a scientist who is also a YouTuber. And, but you recently came out with a new paper about sort of an idea that you've had for searching for extraterrestrials. So let's start there.
Yeah. What's great about this paper is that it was like a day's worth of work. It was one of these things where something exciting happened and my collaborators and I were ready. We had already had the idea, we'd spent a couple of years already formulating the idea, and then nature provided what we needed and we jumped on it. And it feels like in science so often you have to write proposals and spend years thinking about it and building a team and doing the work. And this was one where we could just say like, oh, we're ready. Let's just do it.
Right. So what's the idea? What was the idea that had been rattling around in your brain?
Yeah. So the idea, and it's like I said, it started a couple of years ago. We were laying the groundwork, hoping. The idea is that a civilization who wants to get noticed, who wants to catch our attention or somebody's attention, not necessarily ours, a civilization that's out there that wants to catch the attention of other astronomers would use a conspicuous event, something like a supernova. Or you could also think about like a gamma ray burst or a white dwarf nova or something like that. But you would use a conspicuous event that astronomers like us would want to be looking at. And you would use that to catch our attention. So a supernova would go off, and then as soon as the other civilization or the extraterrestrials saw that, they would send a message. And so you'd have supernova and then message from another star system, not from the supernova, from another star system. And so this naturally builds like a little triangle in outer space where you're observing the supernova and you're observing the other civilization, and you can form this little triangle in space.
Right. And I guess what is the triangle? I'm trying to get an understanding about this.
Yeah. So this triangle is defined by light travel time, right? One of the great laws of physics is that the speed of light is constant. No matter where you go, no matter which direction you point, the speed of light is like the ultimate speed limit that we can use to measure things, to time things out. And so we know the distance to the supernova. And thanks to the Gaia mission, We know the distance to the nearby stars to a high precision now, to like 300 or 400,000 of the nearest stars. We know their distance really precisely. And so we know exactly how long light takes to travel from them to us, how long that message would take to travel here. And so we can time out the size of this triangle. We can figure out when that civilization would have observed the supernova. It would have to be before us. They'd have to be a little closer to it than us. And then when their message would arrive, and there's a little timing delay that we can draw that forms this like little magical triangle. This triangle changes with time. And so any stars, any civilizations that are on this special triangle at any moment in time, they carve out an ellipse. And so we call this the SETI ellipsoid. So I think we get a little confused in our terminology. People expect that there's some like magical elliptical bubble in outer space that defines this like perfect place where transmissions can occur. But it's really like this little triangle of like, we used to play this game in the pool called Marco Polo, where like you cover your eyes and one kid is like it, and they yell Marco, and then everybody else has to yell Polo, and then you're trying to find the person without being able to see them, just from the sound, just from like yelling, calling, and responding, trying to like locate a person in the pool. And it's the same kind of game. The supernova makes a signal, or it makes a conspicuous sort of beacon, and the other civilization would use that, would piggyback that timing to say, we're here, notice us.
Right. And I guess the purpose here, the point here is that this tells you where to look, because you know every month that goes by, this star will have just seen the supernova and communicated towards us. And then a month later, that star. And so you point your giant radio telescope that can only look at one star at a time at that one star at exactly the time when you would expect the message to be sent.
Exactly right. It solves two of the three critical problems in SETI, in the search for extraterrestrial intelligence: when to look and where to look. Because it's a big sky, and in principle, we need to search the whole sky all the time. But that's very expensive, and shockingly, people don't want to give us that much telescope time yet.
That I never understand, but you know.
Yet, I say.
Yeah.
But someday. And so, you know, there's three questions, right? You need to know what you're looking for. Well, we've got radio telescopes, and people at the SETI Institute and Breakthrough Listen and others have worked for a long time trying to figure out what are the kinds of signals that we're actually sensitive to, and then which stars to observe and when. And what's great about this magical triangle situation, this ellipsoid that's moving in time, as you said, is it says that at this moment in time, there's like 100 stars that are intersecting this three-dimensional ellipsoid, such that if they had seen the supernova, their transmission, their signal would then be reaching us now. And our uncertainty on that timing with the nearest stars is now down to like days to weeks. And so we can know exactly which stars to monitor. So we had laid the groundwork for this about a year ago, sort of noting that Gaia gives us the distances and therefore the timing precision that we need to make this happen. And then about a month ago, nature provided us the beacon. Nature provided us a really conspicuous supernova in M101.
Right.
And so this
one of the closest supernova that has been seen in a generation.
Exactly. It's the closest type 2 supernova in 10 years. It's not as close, not as bright as the famous supernova 1987A that happened in the Large Magellanic Cloud, but it is very close. And so what's great about this is it was trivial to get people to look at it, because everybody wanted to look at it anyways. Like, everybody's taking pictures of this region of the sky. It's bright. Even with a small telescope, you can see it. I know a lot of like amateur astronomers have taken out their backyard telescope and been able to see this thing, which is really exciting. And what makes it so exciting to me is, if the whole world is already looking in this patch of sky, then that means they're unknowingly doing a bunch of technosignature research. They're surveying the stars that are first going to be able to send that message to us. And so my hope is we'll be able to go back and scrape that data.
And right. And I'm imagining you get this expanding ellipse in the sky of stars that are aware of the supernova, and then they retransmit the data out, and this eventually becomes the whole sky. That eventually, 1,000 years from now, there will be stars completely in the opposite direction from Earth, which will that are 1,000 light years from us will see the supernova and then go, oh, we should tell everybody we just saw it. But now you're back to scanning the whole sky. So I guess the point here is that you're looking for stars that are very close to within the line of sight of the supernova and happen to fall within the kinds of telescopes that are already watching this region anyway.
That's right. So right now, this triangle is very, very skinny. It's a very skinny ellipsoid. It only reaches out a couple degrees away from the supernova for nearby stars. And so that's right. These are systems that are like almost exactly along the line of sight towards the galaxy M101. And these stars could have then just seen it and immediately transmitted behind them, as it were, and said, like, we saw something, notice us.
Right.
And we would pick
And so
that
what
up.
would you be looking for?
This is the other question, right? We've got the when and we've got the where, and now we have to go back to the what. There's been a lot of speculation about what would be a good signal. I mean, we're piggybacking our information, or this extraterrestrial agent would be piggybacking their information on the supernova. So maybe there would be something to do with the supernova. Maybe they would want to transmit some kind of change in brightness or change in signal modulation in the radio, or say, that had something to do with the supernova, that maybe had the same time scale, or maybe it was a miniature version of it or something. A lot of the signals that we look for are narrowband radio emissions, maybe pulsed or maybe modulated in frequency. And so in this work, what we've been able to do quickly is grab time on the Allen Telescope Array primarily to survey these stars and to do little snapshot observations of them. We're going to come back and do it again and again over several months to see if anything changed, right? Maybe the signal is not a big blasting, we are here, in some narrowband emission. Maybe it's some slow modulation that changes over a period of time, sort of like the supernova itself does. And so we're going to come back and do sort of a time-resolved reobservation over a few months. And I think that's going to be one of the special things. We'll be able to follow up and not only report that we chased these stars, but that we watched them for a little bit of time. And a lot of SETI observations are just snapshots.
But the vast majority of these telescopes are going to be outside of the radio spectrum. You're going to have Hubble Space Telescope. You're going to have probably JWST. You're going to have ground-based telescopes. You're looking at infrared. You're looking at visible light. You're looking at ultraviolet. There are ways that alien civilizations could be communicating at us with those wavelengths as well.
That's right. And I think that's where a lot of the opportunity space in the future lies, especially when we're talking about, okay, not quite the whole sky at once, but a lot of the sky most of the time. Right now, we already observe most of the sky every night with visible light telescopes from the ground. And so if we can figure out signals like that are either flashes of brightness or maybe even better yet, dips in brightness. It turns out it's really hard to outshine your star. It takes a lot of energy to outshine the sun. It's quite a bit easier to block light from the star, to use the star to like occult it or eclipse it with some kind of sunshade or something like that. And so you can imagine something like that blocks a star and does sort of a Morse code type signal or has some kind of conspicuous modulation of the light. That's something that we'd really like to look for. I think we have the capability of doing that with optical telescopes over almost the entire sky. You said something a minute ago about 1,000 years from now, stars across the sky will be sort of intersecting this sort of magical ellipse or a magical triangle. And that's what makes me really interested in this technique as well is, okay, right now we're looking at a narrow cone towards M101, but supernova 1987A, that was more than 35 years ago. There are stars that are really close that have, 35 years, that translates to 35 light years. That's just really not very far in a galaxy that's tens or hundreds of thousands of light years across. And so there are really nearby stars which have just seen supernova 1987A and gone, wow. And if they were ready to send a signal, we could just be receiving that now. And so it's never too late to sort of join this effort with our telescopes. This is my pitch.
Right, but the where to look starts to get fuzzy again as the time goes on and the light from the supernova has reached farther and farther.
Not for hundreds of years. That's the great thing is, again, there's stars within 50 light years that are still that are still optimal for looking for signals based on 1987 event. It comes down to how well we can measure their distance and therefore how well we can predict when that signal would then arrive.
And closer
And
stars are easy to measure their distance.
exactly. So as long as within a
Right.
few hundred light years, we've got a really good measurement. Now, this
Right.
is really
And
hard if you want stars that are halfway across the galaxy, but
yeah.
that's going to take 100,000 years anyway. So
Right. But I can sort of imagine that there's sort of like, on the one hand, you've got the stars that are, are really well within the line of sight of the supernova. And so theoretically, that triangle difference in time is going to be within a certain range. But then you've got those stars that are around us in a sphere that we know their distances very accurately. And so theoretically, you could measure, as you say, to within the day or week when they will have received the signal from the supernova, retransmitted, and that signal will have made the journey to us, and we'll be able to confirm it. And so you just have this laundry list and go like, now look at this star, and then on this time, look at that star.
Yep.
And it
Exactly.
constrains the search. Yeah, that's interesting.
So you can play this game, okay, that supernova's more than 30 years old. You could play this game back in time. There's a lot of historic supernova that have been observed hundreds of years ago.
Yeah.
You can play this game really far back in time. But then you start to reach this limit of, well, once you reach a few hundred years, then you're having to make the triangle out to distances that the timing becomes too fuzzy. And so I've got a student who's got a paper in progress where we're exploring the limits of this with historic supernova, like Kepler's supernova, the supernova that formed various known features in the sky and radio features, and it becomes really hard after a few hundred years. So I would not right now recommend we do this with supernova from 1,000 years ago. That's not quite right.
Right, but supernova 1987A, for example, was the most significant event, cosmological event in our vicinity in 400 years.
Yeah, centuries, exactly.
Right. So it's like and so it is, in theory, everyone in the galaxy should be having a celebration for this moment, using this as an opportunity to go look over here.
There's a really interesting anthropological question about what is an interesting time scale, right? Is once a century rare enough to be the noteworthy beacon that you would want to transmit your signal around? Is it once a millennium? Is it? But maybe alien civilizations have a much shorter time scales. Maybe their lifespans are very short, and so something that happens once a decade is super notable to them. Or maybe they're extremely long-lived, and so once a century is very boring. Maybe they've all seen several supernovae and they don't care. So there's definitely a human timescale that we can't get away from. On the other hand, we also have to operate on a human timescale because that's how our work functions. And so it doesn't do too much good, I think, to worry about, well, this only happens once a century, and so maybe that's not interesting enough, because that's as interesting as we can really get. It does make me think, though, that this endeavor the timescales in which we're searching may be completely mismatched to our lifetimes, right? This finding life in the nearby universe, it may just take 1,000 years. And for us, that's like a really long time scale.
Yeah, we don't have patience.
For them, it might not be. So it's necessarily a generational endeavor. And, we're talking about supernova 1987A. Okay, well, I'm dating myself a bit here, but I was 4 years old when that event went off. And so it's cool that we can still study that it's still relevant to us. But for most of astronomy, that's kind of old history. 35 years ago or so, that's old hat at this point. This may just take 1,000 years, and we have to just be comfortable with the fact that what we're doing requires a legacy. We have to do things, we have to publish them. And that's exactly why we wanted to write this research note, is that we had this idea that we could do this for the first time with survey telescopes and rapid follow-up. And we have Gaia now. We have all the pieces, we think, to do this. And now we have to just do it for the rest of our lives.
Right, yeah. But it sounds like there's the two parts. The one is the opportunity where the event happens and all of these telescopes around the world are collecting all of the data. And now you just have to sift through that data to see if there's another signal that is piggybacking along. And then you've got the other one, which is this gigantic laundry list that starts out precise and gets fuzzier over time with dates and times to make observations of these different places. And
That's
eventually,
right. And at any given time, there's 100 or so stars that we should hit. And so it means if you've got a survey telescope or something or an archive to go through, at any moment you've got about 100 stars you should check. And so this becomes a perfect problem for a big survey or a big computer to just chew on.
Right. And we're going to talk about a telescope that could generate mountains and mountains of this kind of data. But I want to talk a bit before we get into Vera Rubin, which everyone knows is like my most excited telescope. I'm talking about sort of like this changing perspective on being a SETI researcher, because that is not your specific skill set, but you can't help yourself.
That's I think that's an accurate summary. That's right. So by training, I'm a stellar astronomer, and so my PhD was all about looking at variable stars, looking at little stars that flare and have explosive events, so explosive sort of transient events on small stars, looking at slow modulations and changes of stars over many years. Which was driven by things like Kepler and now TESS, exciting missions that were searching for exoplanets and looking at variable stars across the sky. Really exciting stuff 10 or 15 years ago. It's still exciting. we're still doing it. We're still publishing on it. But about the same time, the community started to take a slightly new approach or a new view of SETI, of the search for extraterrestrial intelligence. A lot of this is driven by a decades-long push to study astrobiology. And the field and NASA and others, I think, should be really commended for lifting up this new practice of interdisciplinary research that brings together chemistry and biology and atmospheric science and astronomy, and puts us together to make predictions about what other planets would look like and how we would definitively detect life. And it's a really hard problem. We launched this whole JWST to try to address it. We launched TESS to try to find planets that we could possibly study. So it's already a 25-year, ongoing concern about trying to find planets we could find signals of life. There's, I think, a growing argument that the signals might not be from methane. The better signals might not be phosphine or other chemicals which may have other origins, may have other pathways of being created. And instead, maybe the better signal, or plausibly the better signal, would be technology. The cool thing about technology is the signals, we have almost an unlimited amount of energy we could plausibly put into technology. If you gave a civilization enough time, they could generate almost infinitely large signals, in principle. And those signals could last almost forever. You could imagine a lighthouse that's put in space that runs off of solar power and is just left there forever. It could just keep blinking for all time. So it doesn't, humanity may destroy itself at some point. The sort of the Drake equation suggests that maybe we are not going to live forever as a civilization. I hope we do.
Yeah.
But our technological impact may well outlast us, right? Things like the pyramids, things like ancient artifacts are these sort of one-way messages through time that show us that technology can vastly outlive a civilization. And what's great,
you put a triangle into orbit around the sun, and it's there for a billion years.
Right.
And it is an unambiguous signal that somebody made something weird and put it around a star.
Right, exactly. Now, sci-fi is replete with ideas about, archives that are sent into space or time capsules, things like that. There may be lots of ways we look for these kinds of artifacts or signals that are technological in origin. But what's cool is they are unambiguously a sign of life. And we can debate about, and in fact, last week at the Penn State, this last week at the Penn State SETI Symposium, we discussed a lot about what is the nature of intelligence and how much should we sort of unbias our understanding of what an intelligent civilization is. There are many reasons that species would come up with technology which may not appear intelligent to us. And so there's a lot of bias that we bring to this discussion of what is quote unquote intelligent. But what is unambiguous is that nature does not produce iPhones without life, right? There are just signals that nature does not seem to produce that life does. And we produce a lot of them. We are using a few of them right now. And these are things that nature doesn't produce. And so if you detected something like this, if you detected a podcast, it would be an unambiguous signal of life, whether you liked the podcast or not.
Right. So, I know the paper that you are sort of mentally thinking of, and this was a couple of months ago, someone saying, and maybe it was you, but sort of a combination of your regular cohort saying, actually, technosignatures are the most useful, most unambiguous signals you're likely to get. That astronomers are going to argue about biosignatures in the atmospheres of exoplanets for decades, but you get one podcast, alien podcast, and the debate is over.
That's right. This is why, like Jason Wright has said, and I think this is exactly the right way of putting it, that technosignatures are biosignatures, and thus SETI is a branch of astrobiology, effectively. And I think that shift in mindset has really helped the community embrace this. And so 10 or 15 years ago, when I was a grad student even, we talked about looking for aliens in surveys and looking through our data for signals of spacecraft. And people kind of awkwardly laughed and said, probably you shouldn't work on this. This is not like quote unquote good science. And I had a friend who said, don't do this. This is like bad news for your career. And now it seems like it's still a little out there. I think there's still some of my colleagues who can't understand why we don't all just study dark matter. And like, fair enough. It's fascinating and it's beautiful and amazing. But like, as the community has really shifted to think about life and all the complicated ways that life is going to imprint itself in the universe, this idea of technology is really starting to open people's eyes. I think a lot of my colleagues now are accepting of the idea that maybe this isn't the bread and butter for most of us, but at least some of us should think hard about it.
I think about it like this. Like, if I took these two questions, are we alone in the universe, and what is the true nature of dark matter? And I put them in envelopes and I sort of pass them across the table. And one is labeled aliens ? And the other one is dark matter ? And even the most seasoned dark matter researcher, and they have to like look between these two envelopes and decide which one they're going to open up. I'll bet they open the aliens one.
I think you're right. Also, because if you can make contact with the aliens, they might be able to answer the dark matter question.
Of course, because like it's the beginning of an enormous amount of information that comes your way. That's right. A second perspective to think about these ideas, all of this kind of stuff. It is, like, I say, it's the most important scientific question that humanity has ever asked. I'm waiting for people to give me another one. People are like, oh, I don't know about that. I'm like, okay, like, give me the one that hits at that same level, that is a scientific question. And I do think it is a scientific question. And so I think it's I spend a lot of time thinking about it, like you, and I don't have any academic.
Right? We all want to know if we're alone, right? Like it is a fundamental, like it's somewhere deep in our lizard brain about, are we alone? Is a very human thing. We want to explore. Yeah. We want to see and go places, and we want to know if there are other people like us out there. Maybe the sad part is we might learn that there are other people out there, or people like things out there. We may never be able to talk to them, but even just knowing, I think, is comforting. Right? Even if you just knew.
I always feel like it takes the pressure off us. That, like right now, I feel like we are, for all we know, we could be the only intelligent civilization that has ever appeared in the observable universe. And that we have a few hundred years to get our act together or not. And wouldn't it be just awful if we arose, got to a level of went to space, and then messed it up, and then we used up all the useful stuff, and the octopuses couldn't light fires, and eventually the sun heats up and boils the oceans, and then life in the universe appeared on our watch, and we didn't. So if I see aliens, any kind of evidence of aliens out there, then the pressure is off.
Yeah.
Us to be the ones who don't mess this up.
I feel good. It's a big universe, right? There are a lot of stars, and life is super robust, right? Like, it was the old Jurassic Park quote that life will find a way, right? Like life is very robust and very sneaky. And, probably the limiting factor in this is our own imagination, right? Like, within a few hundred light years of the sun, there are 300,000 stars. And we can't even search them all. It's only 300,000 stars, right? Like, it's a major city. That's it. And we can't even like keep track of all of those constantly. We can't even search them every few nights. And so we're barely searching this like vast ocean of information that's out there. You know, a lot of people, I think, get down on the idea that, look, we've been doing SETI since the 60s. Why haven't, you know, where are the aliens? And it's like, well, they could be screaming at us and we just haven't been looking and listening.
Yeah, they're waving their arms really quickly, hoping we'll detect the gravitational waves.
That's right.
And we haven't seen them yet.
Or they're blinking lasers at us and we just don't have the right cameras that pick up the right laser light. I mean, like, the beacon could be there.
And it's funny, like, we're seeing this rise in a fascination with UFOs and UAPs, and we're seeing people at Congress, and we're seeing, you know, there's a new NASA commission that's looking into this, and a lot of fairly prominent astronomers. And like, I get tons of comments in my YouTube comments, and I'm sure you do as well, about people who are like, what about the this sighting of a UFO? What about that one? And like, although I disagree on that being sufficient evidence to convince me that we are not alone in the universe, I get the drive and the fascination and the excitement and the hope that this is real, because back to that point, that there's nothing more exciting than us making progress on this.
We had a couple of noteworthy here in Seattle, a couple of noteworthy Starlink sightings in the last couple of years. So a few, like, you know, these trains where people could see them and kind of freaked out, right? People were posting on Twitter like, what is this thing? Is it the end of the world? And we had one where a piece of one of the Falcon 9 booster pieces burned up sort of over Portland, and people saw it all over, and it was, you know, it was a big news. And some people really like lamented, like, oh, we're polluting space. And I think there's an environmental discussion to be had here. But what I loved about it, apropos of this, is that a lot of people looked up, right? Like, the number of people who looked up and said, like, what in the world is that? And their mind immediately raced to, I think, a lot of fascinating and maybe exotic things. The inclination for, like, everybody to look up and wonder is the most natural thing. And it's what makes astronomy, like, the most beautiful science, because it kind of belongs to everybody and it speaks to everybody in a way that, like, you don't need a laboratory to wonder.
I whenever I go to a party or, you know, in some get together, and people say, like, what do you do? I'm like, well, I'm a science journalist. I focus on space and astronomy. They're like, I love space. I'm like, well, of course you do. We all do. Everybody loves space, right?
It's like wired into your head.
The flat earthers love space, right? They wouldn't be jumping into the comments and being so excited about it if they didn't love space. And everyone loves space. And so I think even when I get like some nasty comment on the YouTube, I'm like, come on, you love space. I know. I mean,
because we can do both things, because we can do all the important things here, and we should, and we can solve all of our problems on Earth. And also we should look up, and we should wonder, and we should ask, where did we come from? Where are we going? Are we alone? These fundamental questions that I think most humans have wondered at some point in time. And if there's a way that we can work on that. So you asked about the stigma and the sort of cultural bias within astronomy about making these studies, about doing this work. And it's the thing that I hope, by having these conversations, by publishing these papers, you know, we submit grant proposals knowing that the likelihood of them getting funded is like 1%. But we do it to help push the conversation, because we submit the grant proposal, and then our wise colleagues have to read it and think about it. And maybe we change the minds and the hearts of our colleagues just a little bit and say, like, oh, that's actually a good idea. This should be done. And we change that conversation, and we push that window of, I think, how much we're allowed to dream.
And it is interesting that it's, you know, you are suggesting ideas that are, because you have so little in terms of credibility and resources to acquire to do this, you are being forced to get really clever, really resourceful, really dig deep, and come up with really clever ideas. And I think of all of the fields that you're watching, the astrobiology, and specifically this kind of SETI community, has just got banger after banger of really clever idea that you read that and go, that is genius.
Yeah.
And it was same with yours. Like, I saw your paper and I was like, okay, yeah, right. Use all the telescopes that are already observing this event to see this thing. And the data's already there. All you got to do is study it and use this idea to give people some places to look. And I think it's out of necessity.
That's it. You have to be clever. And that's what we learned a long time ago with even just the bread and butter astronomy of like, there are these surveys, there are these telescopes that will get funded to look for dark energy. But in the meanwhile, they're going to survey a couple tens of millions of stars that are in the way. And there's a lot of science that we can do with those. And that, I mean, that's how I cut my teeth of like doing the science with the garbage that people didn't want. They're like, oh, these stars, they keep falling into our spectrograph. Why? We got to figure out how to get rid of them. And we were like, we'll take them. We'll study them. We ended up with like 10 million of these stars that were really useful. You got to be clever. You got to be resourceful because all you can do is look.
Yep. Let's talk about the tool that is about to come online that is hopefully going to revolutionize everything, and that is, of course, the Vera Rubin Observatory. So, like, what is your relationship to this telescope? How are you playing a role in its development and operations?
So, I'm a member of the science collaborations that are doing a lot of preparatory work. So, there are thousands of scientists who are already excited about this telescope and have been for a decade and have formed these really rich science collaborations that are really active in sort of every major area of astronomy. We've got time domain astronomy, we've got extragalactic, there's statistics, there's solar system science. Sort of every major domain in astronomy is excited about this facility because, as you said, it's going to be this tide that lifts all boats, right? It's going to be this wealth of data, and it will be public data almost immediately. And so this means that we're going to get revolutionary volumes of data at a cadence that we're just not used to. So there's a lot of concern that we're going to just be drowning in this data. It's just going to land in about 2 years, and then it's just not going to stop. It's a 10-year survey of the sky. There's a lot of software that runs behind the scenes that takes the pictures, that processes the images. And so here at the University of Washington, we have a bunch of the developers that sit on our floor that work with us that are building those pipelines and those software tools to capture the images, to characterize that's a galaxy, that's a star, that's a fuzzy moving thing, it's probably an asteroid, that take them, put them in the correct bucket and process them. They have to do that within 60 seconds of the shutter closing. They have this incredible requirement that anything that changes, that is we call variable or transient, that changes, has to be published publicly within 60 seconds. And so there's 10 million of these things a night, supernova, novae, variable stars, moving objects that are going to pop into our field of view every night and immediately going to be published to the world. And so a lot of that software work is being done sort of down the hall from us. And we get to collaborate with them. We get to say, okay, what exactly is that data going to look like? And when it comes out, what is in this column of that field? And we get to work sort of hand in hand with them to think about how will we utilize these tools as soon as the data starts flowing.
And so give us a sense of the capability of the telescope itself. Like what, when you think of other observatories that we're familiar with online, there's the Keck observatories, the Geminis, the Very Large Telescope. How does this sort of scale against those mighty observatories?
I mean, it is a properly large telescope. It's something like the 8th, maybe 7th or 8th largest mirror in the world in the optical. So it's already like, it's an easily top 10 sort of piece of glass staring up from the ground. It's also probably one of the widest field telescopes. It's definitely the widest field of view telescope in that class. So the telescope has this funny short design where it's very squat. And that serves two purposes. It means that it gets this wide field of view based on how they've sort of made the optics of the telescope. And it also means that the telescope is short and therefore it's easy to move quickly. If you wanted a very wide field telescope, you'd need sort of this long barrel, and that would be very hard to move, right? You've got something that is the size of a large building that you have to move, and you want to be able to move across and track the sky really quickly. And so you want to be able to go from one end of the sky to the other within a minute. And that's a huge amount of metal and glass to move. And so like nuts to bolts, this is like one of the most sophisticated telescopes ever to be pointed at the sky because it can just whip across the sky absurdly fast. This means that it can take snapshot after snapshot, bang, 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 and cover and tile the whole sky. And so within every 3 days, it will tile the whole southern sky over and over and over. And it'll do that for 10 years. And so this provides this like wealth of data of 10-year survey over and over. You get something like 800 to 1,000 visits for every single star in the southern sky.
And like, I know there's been a lot of papers. I see paper after paper after paper where people are predicting the kinds of things that they could potentially see. Give us a sense of the kinds of discoveries that that you think will be made on the regular?
I think, in the first year of Rubin going online, LSST, so this stands for the Legacy Survey of Space and Time. So within the first year of that survey, the LSST survey commencing, we're going to double or triple the number of small bodies in the solar system that we know about. So these are asteroids, comets, Kuiper Belt objects, things like that. We're going to double that.
Planet nines.
Well, that's right. So of the things that we know we're going to find out there, like asteroids and little dusty, dirty rocks that are floating out there, we're going to double that number in the first few months.
Double. So we have spent 100 years finding comets and asteroids and Kuiper Belt objects. And in a couple of months, we will take that number and we will double it.
We'll double it, and we will fill out like our number. Like there will be hardly any place for these things to hide after LSST has surveyed the sky for the first couple of years. After it's had time to go around the sun a couple times, here parked on Earth, and survey the solar system, there's almost nowhere these things can hide at this point. And this means, exactly as you said, if there is a Planet 9 out there, it's going to be very hard for it to hide from us. LSST has a big enough mirror that it should be able to detect it, even if it is extremely cold, even if it's small and cold. Things like Pluto and these other large objects that are in the outer solar system, they're way too bright. They're going to be ridiculously easy to detect. And so if there's anything like that hiding out there in the outer reaches of the solar system, hundreds and hundreds of astronomical units away, it's going to be very hard for it to hide. So we're going to know within the first year or two whether or not this Planet 9 is actually there. I'm not a dynamicist, so I don't have a good hot take on whether or not I think it's there.
Right.
but I'm very confident we'll be able to rule it out if it isn't.
Yeah, just trust in Vera Rubin at this point.
That's right. You trust in our measurements. That's right.
Yeah, you don't need to have a prediction conversation about it anymore. Just wait.
And it's not that long. We're going to know. Yeah. So, that requires a big mirror to gather faint objects, to detect faint objects, and you have to survey the whole sky, right? You can't just look in one little window. You need to look over a huge range of sky. This means that this is the perfect telescope to look for counterparts to LIGO and to gravitational wave events, right? We don't know exactly precisely on the sky where these gravitational wave events are occurring. We get sort of rough localizations. We know they're sort of in this quadrant of the sky. You need a telescope that can scan that entire quadrant of the sky down to a really faint depth, and you need to do it fast. It's the perfect telescope to follow that up. It's also the perfect telescope to make the deepest map of the edge of our observable universe. Okay, JWST does a better job in the infrared. It's an infrared telescope. It can go further back in time as a result. But JWST's field of view is really small, and you're not going to be able to make a map of the most distant galaxies, the most distant quasars in the universe with JWST. You just don't have, you would take hundreds of years to tile the whole sky to sufficient depth with JWST. LSST, this is its bread and butter. We're going to be able to survey that outer edge of the universe to, we would say, redshifts of like 10. So into the very first sort of hundreds of thousands of years of the universe, we're going to be able to map where the galaxies are at that really distant age. And this is going to give us measurements on how much the universe has expanded. Is there a period of inflation that happened? Is the universe accelerating, which we think it does? How universal is that acceleration? It's going to be amazing. And I love this idea that we're going to use it to search for aliens. We're going to use it to search for comets and asteroids. We're going to use it to search the Milky Way. 17 billion stars in our Milky Way. That's something like
20%.
10 to 20% of all the stars in the Milky Way we will have a good picture of. And then we'll actually study the nearest galaxies and the furthest galaxies all at the same time. Yeah,
there's one interview that I did where he was saying, since Type 1a supernovae were first discovered, astronomers have painstakingly collected about 1,500 of these things across the universe. And Vera Rubin should turn up 1 million.
Yeah. Yeah, you start to say things like all of the Type 1a supernova we've used as the quintessential ruler to measure the expansion of the universe. That will be a month's worth of work.
Yeah.
Like the last 30 years, Nobel Prizes, all that, that's a month. No problem. And we'll just keep doing it.
And so from a technical perspective, you've got this telescope is doing a lot of the, or I guess the computers underneath are doing a lot of the work in advance for the astronomers to turn what would just be a a fire hose of raw data that they'd have to dig through. It's going to try to identify interesting stuff as the images are coming through the system and then putting those out into a separate database. Is that sort of the plan?
Yeah, so you've got this real-time component, right? Again, anything that explodes or moves or changes, 10 million of those things a night, it's going to flag and publish those in a data set within 60 seconds. That
right, so those are the highlights.
That's the highlights. But even that is like overwhelming. 10 million a night. Like, there's not enough telescopes in the world to chase them all. You have to sort them, right? If you've got hundreds and hundreds of supernova every night, you need to know which one you could possibly chase. Like, what's the most interesting one? Because the only other telescope, okay, this thing's 8.5 meter mirror. You need a big telescope to follow anything up, right? So you're going to have to go beg some time on one of the other 10 largest telescopes in the world to follow up one object out of millions of interesting things per night. So yeah, the software challenge to find the most interesting thing is like monumental.
So is there a highlight of the highlight? Like, is it going to try to identify really interesting things?
The challenge lately has been simulating this kind of data to see how quickly can you find the most rare supernova or the most rare transient event, or how quickly can you associate this moving object with an interstellar comet, for example. Can you say, how quickly can you definitively say, yes, that's on an interstellar orbit? It's really hard. You can't do it with one or two measurements. You need to be able to piece together its orbit. And so pushing that limit, right, using tools like AI and machine learning to say, okay, what are the probabilities that this brightness of this object in this color says that it belongs to this extremely rare category of thing? And how quickly and how definitively can we make those kinds of assertions? I think that's what a lot of the action is this year, is building that tool and building that training set. And it's very hard because we don't have a LSST to practice on.
But there will be people looking through the waste material for everything else. So the raw data will still be there and available for people to dig through.
Yeah, that's right. So within 60 seconds, the most flashy whiz-bang things happen. And that's exciting. Again, I did my PhD studying flares, which happen over a course of minutes to hours. There's going to be a zillion flares, approximately. And that's amazing. And at some point, we'll just keep collecting them and say, I don't know, let's just put it in the bucket. We'll figure out what to do with it. But then what do you do, right? When you have 17 billion stars, are any of them interesting anymore? Like, you have to start really teasing out what's unusual. And what excites me about this survey, not that I'm not excited about the 60-second alerts. I think they're fascinating. And especially in that first year, they're going to be really exciting. What really excites me in a deep way is the 10-year aspect of this survey, is that not only do you have this amazing, deep resource of data that scans this huge portion of the sky, but you're going to do it for a decade. And that, as I get older, that element of patience, I think, is starting to really weigh into my work, is that we're going to have these measurements. There are stars that are going to be changing by a few percent over 10 years, and we don't know why, but we know that that will happen. We've seen a few stars change like this over timescales that are very slow, and this goes back to like 1987 was only a few decades ago. This is nothing in the lifetime of the universe or in the lifetime of a star. We're going to start poking at this interesting time scale of 10-year time scale, decade time scale things. And we're going to have this facility. I mean, hopefully it's still running. Hopefully after 10 years, they get funding to do another 10 years. We're going to have a really interesting conversation, Fraser, in 10 years, where we say, like, there's all these exotic things we had no idea the stars do on decades time scale. And we have no prediction of what they are.
There was this, we did a couple stories this week actually about these young stars that have hot Jupiters and they are lighting them on fire. They're so close that they're hotter than stars on their surface, and they are pushing out these envelopes of helium around them, and they're not long for this universe. And they flare on a cycle of a couple of 100 years. They go from nothing to suddenly problem for the planet, and then the planet is gone. And astronomers know of a couple of these, and so astronomers will now know of a few thousand of these.
And there's a sample of things we call red novae, which are probably, I mean, we only have a couple of them. Probably they are stars that are colliding, right? Stars that are binaries, lots of binary. Half the stars in the universe are binaries. There's nothing unusual about that. But that the binary got close enough that the stars started swapping material back and forth, and their angular momentum just completely went berserk, and the stars ran into each other. And when they do, you get this really dusty red explosion. We don't know what comes out the other side of that. We have models, but we've only got a couple examples of these. There's a really famous one from about 2011 that went off in our galaxy. And we managed to catch it as it was inspiraling and the two stars were falling towards each other. And then this huge explosion went off over several months. We still don't know what will emerge from that. It's still like enshrouded in dust. And there's only a few of these known. How many will we see with LSST? How many will we see on that in spiral? And we'll be able to actually make predictions of when that collision will happen. I don't know. It could be thousands of them.
And so if a future you or some version of you that has a really clever idea for doing a SETI related search through the data, I mean, can you envision a person going, okay, I think that an alien civilization might want to have a triangle floating past their star and it would give a very specific signal. Can I look back through the LSST data for this specific signal? Is that a feasible operation that a person could run on however many exabytes of data there are?
Absolutely. Both because, as the name suggests, it's the legacy survey of space and time, right? So this is not only a survey about discovery in the next 10 years, it's a survey about laying down a foundation of observations for the next century. And so making sure that the data is archived, that every pixel is saved, that every photon that we collect is saved and tagged, and we understand it, and we understand what the software does to it. Someday, halfway through the survey, somebody's going to come up with a better idea of how to process the data, and they're going to go back to the very first images and reprocess the whole thing. We know this from other surveys, that we get more clever at handling systematics and reprocessing and pushing the depth limit, pushing the precision of the telescope. So the software will continue to improve even over that 10 years. And it means that you can go back after the shutter closes for the very last time and say, all right, let's take 10 years of data and see what's hiding in the slow time domain, not just the rapid time domain, or let's posit a new idea about how spacecraft might move through the solar system and check another little corner of parameter space for a Star Destroyer moving through the through the outskirts or whatever.
Yeah. But it's interesting, like when you think about, say, like when the Apollo samples were brought back from the moon, they studied a bunch of them, but they also put a bunch in deep freeze, knowing that better scientific instruments were going to come online into the future that they could then study and get answers. And if they don't crack them all open, then they wouldn't have been available to the future instruments. And I kind of like that idea. Now, you mentioned the shutter closes for the very last time. The shutter's never going to close. Come on. They're just going to renew it, right?
I mean, they're going to have to put a new shutter in eventually, but yeah.
Fine. But it's a ground-based telescope. You just go over and you give it a hug and you give it a new shutter and you move on to season 2, right?
That's right. And that's what's so great about it. Yeah, it's a sort of billion-dollar class instrument and it's taken a long time to build, but it is so much cheaper and easier to fix than anything you put in outer space. That's right. So right now there's no plans for an LSST-2. But there's a lot of discussion already. Before we've even taken the first images, there's people already debating, what else should we do with this? We have this really unique piece of glass. What else should we do with it? And maybe it's putting in different filters. Maybe it's pushing it further to the infrared. Maybe it's take all the filters out and just gather as much light as you can, or put a really narrow band filter in and just look at like the hydrogen alpha line or something like that. And we've never done a wide field survey of the hydrogen alpha line like that, for example. There's a ton of possibilities, and my hope is that with the smashing success of this program and 1,000 papers a month coming out or something, that we'll never be able to read them all.
Well, the AIs will be generating the papers and reading each other's papers.
Oh no!
Right?
Oh no! My hope is that we sort of develop this ecosystem of like careers that form around this data, and that we get really good at figuring out what are the most interesting objects to chase. There's always going to be a place for the astronomer proverbially sitting at the telescope, taking the image or the spectrum of one star. We just need to get better at figuring out which star or which supernova that is. And the software and the AI, it's going to help us like whittle this sample down because it's going to be overwhelming at first. What's nice is Moore's law suggests that our ability to process the data will get easier and easier. So when they talked about terabytes of data a night, when I first heard this years ago, I thought, oh my goodness, I've never seen a terabyte of anything. And now it's like, all right, I mean, I probably am downloading a few terabytes on like Netflix every few days. Like
Right.
I'm streaming this much content. Like it's just not that terrifying anymore.
You could
So
download
petabytes
the
of data.
entire thing. Yeah, you could download the entire thing on your local computer, process it, and dump it, and stay up on top of it.
You can't now. Right now, they're building a small supercomputer cluster on the summit next to the telescope to do this real-time processing. But you can guarantee that, like, you know, my laptop or my desktop computer at the end of the survey will be like, all right, yeah, it's a little big, but we can do it.
Right. Well, what about north? Because like the downside is you only get the southern hemisphere.
Yep. Yeah, this is a challenge. They can only go up to about 20 degrees north. So there's a big chunk of sky, something like a third of the sky that it just cannot reach. Now, thankfully, we've done a lot of work there already, right? So the Sloan Digital Sky Survey and the Zwicky Transient Facility, those are all sort of closer to the north or near the equator. So they have done a lot of work in the north. But someday we would like to have North and South Rubin observatories or something like that. I think that would be really cool. My secret hope, let's go back to the top of this interview. My secret hope is that we actually start watching the whole sky all the time. And to do that, we have to get rid of this pesky sun coming up thing. This requires going to space. And so my hope is at you know, somewhere in my career, we start seriously planning, you know, a NASA mission or something like this that launches a fisheye lens array into orbit, and we can actually monitor the entire sky all the time. I think that's the next frontier of the time domain, but also in like the solar system and you know, so many other parameters of astronomy that need to monitor everything. You don't know where the discovery is going to come from.
Yeah, the data transfer sounds like that would be the nightmare. That's
right. And if you want to observe literally the whole sky, you have to go on the back of the sun, right? You need to be on the other side of the solar system to observe the side that we would call daytime. So we need multiple ones of these facilities, multiple of these sort of fisheye facilities. And we got to get the interstellar internet beefed up a little bit.
Right. I can imagine this thing sort of firing hard drive projectiles towards Earth once a day, right? It's just firing these little nano drives our way to try and get the
thumb
data
drives
back home.
flying through space. Yeah, that doesn't sound dangerous at all. Yeah.
No. What could go wrong? What could go wrong? But what do you think, like 20 years from now, there is the Vera Rubin in space. There is how does that take it to the next level, do you think?
Well, I mean, the moon is a really interesting platform, right? Where you can get things and it's fairly stable. Doing wide field in space is always the dream. I think Roman is going to push that envelope quite a bit. Roman has about 100 times wider field of view than HST. That's really interesting. So there's a lot of people thinking about wide field surveys with Roman as kind of a next step. The cost just has to come down a lot, you know, factor of 1,000 or something. It has to come down a lot to make this anywhere feasible. Rubin works because, as you said, we can drive up there, we can give it a hug, we can swap out cables, we can write new software, and we don't have to like send a spaceship to change the mirror. The mirror can be taken out and re-illuminized and recoded and fixed. And the ground is always going to be the better place to work from like the engineering standpoint. Space is just super duper hard.
So give us the timeline. So what are the major milestones that we should expect from, you know, we're recording this the end of June 2023.
Yeah.
What is the next big milestone that everyone should be looking forward to?
So what I'm looking forward to right now is the last piece of major hardware arriving in Chile, arriving on the summit, and that's going to be the camera. So the camera is functional. It's built, it is in really good shape, and it is in California currently. They had a couple more delays in terms of getting it buttoned up and getting ready to ship. It's going to take it a couple of weeks, I think, to get down to the summit. They have to rent a 747 and fly it, and then get a special truck, and it's a whole operation. It's the largest digital camera in the world. It's the size of a jet engine or a small truck. And so it's a major operation getting this huge piece of hardware, but it's the last big piece of hardware that is needed on the summit. The mirrors are there. All the computers are there and running, and they've been running tests on the computers and the fiber optic cables. So everything else is ready. We're waiting for the camera. It should be down and being integrated onto the telescope sometime in October. Hopefully, fingers crossed, October, we're looking at the telescope actually being fully assembled for the first time by the end of the year. So first light is early to mid next year. So hopefully they get everything in there, they check the alignment, and they get ready sometime mid next year, mid 2024. We will see the first photons, we call it first light, the first photons come from outer space, bounce off the mirrors, land in the camera, and end up on the front page of the New York Times.
And Universe Today. Yeah.
And the Universe Today. That's right.
Yeah.
Exactly.
Yeah.
That's right. And then sometime in early to mid 2025, we think the survey, the LSST survey, will actually begin. I feel very confident that date was supposed to be 2024, but we have had more COVID delays and more hardware delays. The NSF has put a big focus on getting this operational in 2025. So I feel really confident that in 2025, we will have this survey online for the next decade. So that's my prediction, is that you and I will be sitting here in 2 years talking about the very first supernova discovered by LSST, or the very first interstellar object. That's what I'm really excited about. The very first interstellar object in the first month of data, I hope.
Yeah. Well, I will schedule this conversation now, and you will definitely come back, and we will definitely talk about it and just obsess about the first hour.
That's right.
Then, because that's all we'll have time for, is what happened in 1 hour, in literally real time. Oh, could you do that? You could
do it.
Couldn't
we could
you?
do it. If you want to do this at night, we could do it, and we could have the alert stream flowing in the background and be like, look at that.
Oh, that's great. That's an awesome idea. I love it. All right, we'll do that. That sounds great. All right. Well, James, always a pleasure. If people want to follow the work that you're doing, what's the best way to do that?
Probably to follow me on social media. I'm on all platforms, JRA Davenport, and my YouTube channel hopefully will come back this fall.
Great. See the fall season.
Fall.
All right.
That's right.
Take care, James. Stay safe and enjoy our Pacific Northwest summer.
Keep looking up.
Right on. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast, or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Antonio Lofi Lara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltinan, Modzo, George, Jeremy Matter, Jordan Young, Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.